Hi, my name is Jose Villazon, and this is my Physics Lab 3. Of the lab, a little bit of introduction. The purpose of the lab is to predict the circuit behavior with resistors in parallel or series, measure current and potential difference using multimeters, and examine the behavior of ohmic resistors and capacitors. Some models and physics principles that we use in this lab are the node rule, which means that the current that flows into a node must be equal to the current that flows out of the node, as you can see in the pictures below. And then loop rule, the sum of all electric potential differences around the circuit is zero, and again illustrated by the two pictures below. And then Ohm's law, which is V equals IR, which is the voltage equals the current times the resistance, and that's the current through a conductor is proportional to the voltage across the points. A preview of the main result, the node and the loop rule hold true, and the current in the RC circuit is time dependent. Was the circuit in our experiment, our system was the circuit and the surroundings were everything else, and the initial conditions were that one resistor has 47 ohms of resistance and the other has 100 ohms of resistance, and you can see a picture of the circuit right there. So then we had to predict the currents I1 and I2. So adding up the voltages from the two batteries, you get 3 volts, and then we add up the total resistance of the two resistors, and we get 147. And then using Ohm's law, we get we rearrange the equation to get 0.02 amps. So in the actual experiment, we got current readings of 0.0241 amps, which proves that our prediction was correct. Then we tried reversing the connections on one of the ammeters to see what would happen and saw that this didn't change the current readings. Then we switched one of the ammeters to be a voltmeter and observed the following, that the ammeter is still connected to the circuit read 0 amps because the voltmeter has high resistance, and the voltmeter reads 3 volts since there is no other voltage drop. So a little bit of analysis. Then we were asked to find the voltage drop across the circuit, and we got the following. So using the voltage drop equation, setting it equal to 0, we calculated each of them independently, as you can see right there. We got the values. And then once we summed them all together, they all equaled zeros, which was what should happen, which is good. So then further going into this, plugging in the stuff we got, we then attached a voltmeter and we altered the circuit. So why doesn't the ammeter reading change? And that's because the voltmeter has high resistance, so very little current flows through it. Okay, now we place an ammeter in parallel with the 100 ohm resistor. What happens to the current through the other ammeter? The ammeter has very low resistance, so the current will go straight through it instead of the resistor. So this will increase the current going through the circuit and the second ammeter because the total resistance of the circuit is now 47 ohms. This means that the new current for the circuit would be around 0.06 amps. So then now we have to calculate the resistance of each part of the circuit. So using the values we calculated, we can again reorganize Ohm's law, and we get that the resistance in the 47 ohm resistor is 48, which is pretty close, so that makes sense. And then same thing with the 100 ohm resistor, it's 102, which is pretty close to 100. And the wire, since there's just 0 volts in it, there's just, yeah, 0 resistance, and same with the ammeter. And then we made RC circuits and observed how long it took to charge and discharge the capacitor in the circuit. We observed that the 10 ohm bulb took 10 seconds for both, and we observed a 20 ohm bulb took about 20 seconds for both. Then we used the RC circuit and recorded the voltage as it dropped as the capacitor began to discharge, and make an ln versus time graph to experimentally determine the value of RC. So then we have the graph here. So then our predicted RC was 4, but then using this graph, we got an experimental RC of 4.1, which is very close to 4. So that means our prediction is, well, that our experiment went pretty well. Human error in stopping the stopwatch and the capacitor from discharging at the same time. The circuit wires, resistor, and capacitor batteries could have had some wear, making the reading slightly off. For the answers to the what if question, the capacitor would charge the full instantly since there is no resistor regulating the current. This wouldn't happen in real life because the wires and batteries have some internal resistance, which would mean it would take a few seconds for the capacitor to charge up even without a resistor. When actually measuring with an ammeter, we see that it does take a little bit for the capacitor to charge up, and this is due to the reasons above and also that the ammeter has some resistance.